So in this presentation, I will talk about surface matching using a data attachment term that relies on the theory of normal cycles. So I will first briefly remind the framework of inexact registration and the necessity of a data attachment term. And to construct this data attachment term, we will consider surface representation of shapes with normal cycles that are objects associated with the normal bundle of the shapes. So once we have this shape representation, we can define kernel metrics on normal cycles, and this will gives metrics on shapes that are sensitive to the curvature. And I will then provide some example of registration with this data attachment term. So what we want to do here is the matching of geometrical structures. So given two surfaces x0 and x1, so here two retina surfaces, we would like to find a deformation phi that bring x0 close to x1. So to do so, we associate with the matching problem, we associate a variational problem where we want to minimize a functional j that is a sum of two terms, an energy term associated with the deformation phi that will enforce the regularity of the deformation, and a data attachment term A that will measure the residual distance between the deformed shape phi of x0 and the target shape x1. So in the following, I will mainly focus on the construction of this data attachment term. And to construct this data attachment term, what we can do is to embed the shapes in a Hilbert space with an explicit scalar product. So this has been done, for example, by Joan Glones, where he defined a metric on currents, and we have an explicit scalar product between two shapes, so C and S. And this scalar product is the integral over the double integral over the shapes S and C of the scalar product of the tangent vector at point x and y, convolved with a kernel KW that takes into account the relative spatial position of the point. What we propose to do here is rather to consider integral over the shapes S and C, to consider integral over the normal bundle of the shapes. So here we have depicted in green the normal bundle associated with the curve, and the scalar product takes the form of a double integral over the normal bundle of the scalar product of the tangent vectors, convolved this time with two kernels, one spatial kernel that takes into account the spatial position of the point, and one normal kernel that takes into account the normal position, the disposition, the relative disposition of the normal vectors of the point. So by introducing the normal vectors of the shapes, we introduce curvature information about the shapes. So this raises the question of shapes representation. In which space do we consider shapes? So I present here first the representation of shapes and surfaces with currents. So what we do is considering a surface S and a Hilbert space of vector fields, we consider that a surface S has a linear form over the space of vector field through the flux of the vector field across S. So by doing this, we consider S as an element of the topological dual of W, and so S is considered in a Hilbert space W prime. So in fact, the right object is not a vector field, but differential forms, because these are objects that are meant to be integrated over surfaces. So what we consider in the following is differential form, and a surface S will be considered as a linear form over some Hilbert space of differential forms. So the representation of shapes with current is this representation of shapes, considering shapes as elements that integrate differential form. So what we propose to do here is rather to consider currents associated with the shape itself, to consider currents associated with the unit normal bundle of the shapes. So the unit normal bundle of a shape is the set of the spatial point associated with the unit normal vectors at each point x. So here, for example, we consider a dark blue triangle. And at each point of the triangle, we will describe the normal vectors associated with this point. So for a point at the interior of the triangle, we have 2 normal vectors. For a point at the edges, we have a half circle. And for a point at the vertex of the triangle, we have a portion of spheres. So the total unit normal bundle associated here is the light blue part, the red part, and the green part. So notice that we have depicted the unit normal bundle here in R3, but the space where the normal bundle lives, in fact, is R3 times S2. So in any case, the unit normal bundle is a 2 surface of R3 times S2. And it has a canonical orientation that is independent of the orientation of the original shape. And what we will consider and what we define as normal cycle is the current associated with this unit normal bundle, which means that we consider the unit normal bundle as an object that integrates differential forms. So why are we doing this? Well, in 1959, Federer showed that if we consider a domain X of R3 and S its boundary, and be a Borel set, if we look at the volume of the epsilon tube around X, it is a polynomial in epsilon, and each coefficient of this polynomial can be interpreted as curvature measure. So, for example, we retrieve the area form of the surface S, the mean curvature measure of the surface, and the Gaussian curvature measure of the surface. Zeller showed 20 years later that, in fact, this curvature measure can be retrieved with the normal cycle through integration of adequate differential forms. So, by considering the normal bundle and integrating specific differential form over this normal bundle, we retrieve all the curvature information of the shape. So that's why we say that the normal cycle encodes curvature information of X. So now we have a shape representation with normal cycle, and we are left to design interesting metric on this space, and this on normal cycles. So usually what we do is we define a reproducing kernel Hilbert space of differential form. So we construct a Hilbert space through a kernel KW with an explicit scalar product here. And this generates a space of differential form W. And once we have this kernel, we have an explicit metric on normal cycle, since I recall that normal cycle lives in the dual of W. So now we need to choose a kernel that provide explicit metric, and we choose a kernel that is the product of 2 kernel, a spatial kernel Kp and a normal kernel Kn. These are 2 scalar kernels, and once we have this kernel, we have an explicit scalar product between the normal cycles. That is the scalar product I showed you in the first slide. So we are left to choose Kp and Kn, and for this we need to have explicit expression at least for polyhedral shapes, for triangulated surfaces. So here I have depicted the unit normal bundle of a union of 2 triangles. So we see that it's rather complicated. We have a cylindrical part in red, a planar part in light blue, and spherical part in green. To compute explicitly this integral, we can easily have approximation on for the integration on the spatial space, but there are no obvious approximation on the normal space. So we need, for now, we need to compute explicitly the integrals over the spherical part and the cylindrical part, and since it's rather intricated, we need to choose simple kernels. So the spatial kernel, we will choose a Gaussian kernel that is usually used in the community. But for the normal kernel, for now, we will use only a constant normal kernel equals 1. So it may seem a little bit coarse, but in fact, we will see that we retrieve curvature information of the shapes. So this expression is not meant to be read extensively, but just to show you that with this choice of kernel, we have this metric, this scalar product, and in red, we observe a quantity that is associated with the cylindrical parts of the normal bundle. And in green, we have quantity associated with the spherical part, but of the boundary of the shape. So this red part can be considered as associated with the mean curvature of the shape, and the green part is a boundary term that appears naturally in the metric. So now we have an explicit scalar product, so we can fit a representation and an explicit scalar product, so we can fit it in a registration framework. So this has already been explained this morning, but quickly we consider a group of deformation that is obtained through integration of time-varying vector field with finite energy. And the variational problem that I showed you in the first slide can be rewritten in the following way. So we want to minimize the functional that is the energy associated with the deformation, and the data attachment term that will be the kernel metrics on normal cycles. So here we have the deformed shapes and the normal cycle associated with the deformed shapes, and here we have the target shapes. So of course, for now, this is a minimization on an infinite dimensional vector space, but by introducing reproducing kernel Hilbert space and in the discrete framework, this is only dependent of the initial momenta that is finite dimensional. So we can apply a minimization procedure. So here are first example of registration with normal cycles. So the blue sphere is the source shape, and the orange duck is the target. And in the left, we will observe the deformation obtained with data attachment term with normal cycles, and in the right, the same registration, but with varifolds this time, varifolds that are a sort of unoriented version of the currents, where we consider shapes as associated with their tangent space at each point, unoriented tangent space. So this is an unoriented metric as for normal cycles, but just consider the first order information of the shapes. So here are the results obtained. So this is with normal cycles on the left, and on the right with varifolds. So one can observe that the metric with normal cycle, we have better matching of the eyes, notably, and the beak of the duck. And this is maybe more obvious on the next example, where we want to match two retina surfaces. So we want to match the blue one to the orange one. And what we observe with normal cycle is this deformation, and with varifold this deformation. So we see that, I recall that with normal cycle we have a boundary term that appears in the metric, and which will enforce the matching of the boundary of the retina. Whereas for varifold we do not have this boundary term, and in fact during the registration we can observe a pitching of the corners, because there is absolutely no reason that the boundary are matched. So to conclude this presentation, we have provided an unoriented representation of shapes that encodes curvature information with an explicit matrix through kernel matrix, and that fits well in a registration framework. So for future work, it would be interesting to compute the scalar product with other kernels that just the constant normal kernels. So for example, the linear normal kernel will be interesting. And of course, to go deeper in computational anatomy with this metric, and for example, providing a statistical analysis of atlas estimation. So thank you for your attention.
Okay, thank you. Okay, so questions? Okay, so I have one. So what you said is that you are using for the normal, you're using just a constant. Yes, for the normal part.
Yeah.
Yes, you have two parts. You have two kernels, and one is and you say that
Yeah.
okay, kn is equal to
Yeah.
1. So can you say a little bit about that? This is
Why we
what
choose
are the consequences of this? Because you have
Yeah, at first we could think that using a constant kernel we will lose all the curvature information that we have by introducing this normal kernel. But here we have the scalar product of the tangent vector of the normal bundle. So in fact, these two tangent vector contains all the curvature information of the shapes for themselves. But we have studied a little bit what kind of curvature we are able to retrieve with this metric. And in fact, we can show that we can retrieve only the mean curvature information of the shapes with this constant kernel. And and this is what we can see in the metric, in the discrete metric. And if we choose not a constant kernel but a linear kernel, which means the scalar product between u and v, we can show that we can retrieve the Gaussian curvature of the shapes, but we are insensitive to the mean curvature of the shapes.
okay. Okay. So any other questions? Okay, so I think we will close this afternoon session, and thanks all the speakers.